we covered three different transforms. We covered the DTFT, and we covered the DFT, and we covered the Z transform. So let's compare each of these guys. We've got the DTFT, which is x of e to the j omega. Gordon, is that a continuous frequency function or a discrete frequency function?
The DTFT is continuous.
Right. It's a continuous frequency in omega. And if we want to take a look at the forward transform, that's going from the time domain to the frequency domain. It's this sum over all n of our input sequence times e to the minus j omega n. And then we've got its inverse transform. And that's much less used. Let me write that a little bit more neatly.
Except on your labs, right? You know, it's pretty used.
We do talk about in the labs. You're right. But you're not going to find, even on the labs, there's not, I think that there's one section of the lab that talks about it. But in general, we don't do this integral much.
I was just messing with you, sir. It's all, that's all.
Oh. I think there actually is a section in the labs that uses it. But compare that with, yeah, in fact, I'm going to give you an example. And in the examples in class, we always start out with these infinite length sequences. So I'm going to give you an example of a finite length sequence. So let's do this one. 2, 6, 3. So that would look like 2 plus 6 e to the minus j omega plus 3 e to the minus j omega 2. Of course, it's got a denominator of 1. And if it had a denominator that wasn't 1, then it wouldn't be a finite length sequence. It's hard to read this. I'm going to write that a little bit more neatly. Then it wouldn't be a finite length sequence. Then it'd be an infinite length sequence. Now the DFT is that finite or is that, I'm sorry, is that discrete frequency or continuous frequency?
Discrete.
Right. And it's the same length as its input sequence. Since it usually takes a discrete input, so here our sum usually begins at n equals 0 and goes to capital N minus 1. It won't take an infinite length sequence. Because it takes a finite length sequence, it assumes that it begins at 0. And otherwise, it looks very similar to the DTFT. It has an inverse. Now the inverse, unlike the inverse DTFT, which is rarely used, the inverse DFT is used all the time because it's another easily computable sum. Oops. So that's from k, goes from 0 to n minus 1 of x of k. And remember, the only reason why I draw these little bars up and down is to show it's a capital X, to show that we're in the frequency domain. And you'll notice that we have a minus here. We don't have a minus in the inverse, and we have this 1 over n. This is a good time just to mention that if you talk to a mathematician they'll use the same words, but they'll have different functions. Mathematicians, you got to have this 1 over n someplace in there. It could either be up here or it could be down there, and as long as it's one of those two places, you'll have a forward and an inverse that are inverses of them. And mathematicians like to split the difference. They'll actually do something that they define it to look like 1 over the square root of n, and then 1 over the square root of n over here. So the forward and the inverses look almost the same. That's unique to mathematicians. All engineers, whether electrical or mechanical or civil, use this notation. And to find the DFT, all we're going to do is sample this at omega equals 2 pi k over n for k equals, we've got 3 things, so we're going to have 3 indices. I'm not going to write the whole thing out, but it really is that direct. So x of k equals 0, I'll do the first one, is going to be all of this with 0 substituted into here. So omega would be 0, and so we end up getting 2 plus 6 plus 3, which is 11. In general, for your higher order ones, x at k equals 0 is always real because it's the sum of our x of n, but x of k equals 1 will be complex, and it will look nasty. And that leaves us with the z transform. And the z transform is the sum from n equals, it again works with any length sequence, doesn't have to be finite. I'm just going to say don't do. Whoops. There is a integral that exists. It's a complex contour integral, which means it goes around in a circle in the z-plane. Just don't. But man, it makes finite length sequences so easy to compute. And you might wonder why we make such a big deal over the RSC for the Z transform when it doesn't seem to have any real bearing on anything we actually do. The reason becomes more clear in graduate level courses. It's because the Z transform, I don't want to get into it much right before an exam, but every sequence actually has 2 different Z transforms with opposite RSCs. So if one RSC is Z greater than, magnitude of Z greater than 2, the other one would be magnitude of Z less than 2. And those 2 actually correspond to different sequences. One would be a right-sided sequence and one would be a left-sided sequence. And left-sided sequences or dual-sided sequences become useful if you're analyzing in different domains. If you're analyzing, say, pictures, which don't really have, that's a 2-dimensional transform. It doesn't have a preferred direction. There's no preferred direction of time. You can go forward or backward in X or Y just as easily. I'm going to keep it for now that the RSC becomes important at graduate level topics. All right, so that's everything we covered on DTFTs, DFTs, and Z transforms. By the way, Z transforms also continuous in Z, but now they're kind of really weird. Now they're continuous in both. Remember, the Z transform, Z is unlike the omega, which is a real value. So we would graph that between 0 and, say, pi. You could go up as high as you want to. You could go to 2 pi or higher if you want to. You can go negative if you want to. But the point is that omega is a single real continuous variable. And the DTFT, in which k, it's discrete, 1, 2, 3, that's your k. Here your Z is not only continuous, but it's also complex. So you'd have to graph it over a whole region. You'd have to graph it over a region like every place in here. And the DTFT is complex. The output is complex. So if we wanted to graph it like this, we'd have to graph, say, just the magnitude of the DTFT, or we could graph its angle. Same thing for x of k, the DFT. It's complex, so we have to choose, if we're going to graph it on a nice 2D plot, which part of it, the magnitude or the angle. And then the Z transform is also complex. So if we were to graph the magnitude of the Z transform, we'd end up with some sort of surface in 2 dimensions over the input range. Let me talk about about each separately. I think there's room here for me to cover. Am I writing too small for you guys, or can you see this?
We can see it.
We can see that.
Okay.
Sir, can I ask a quick question?
Sure.
You said that we don't do inverse Z transform there. Am I reading that right?
That's correct.
Wasn't our last class about inverse Z transforms?
Yes, but the difference is that you will take inverse Z transforms using tables, but not using a formula.
Oh, gotcha. Okay.
The formula is truly heinous. It's I don't know if you've ever seen integrals that look like this. That means it's taken. That means the. Let me try this again. Yeah, that's a good point, Eric. What I mean is don't do the integral that looks like this, where you're taking a complex contour integral over this complex plane. Instead, just use your tables. That's a good point. Maybe I should don't do this. Instead, use tables. And in fact, I'm going to suggest you use the tables for this as well. Good point. Okay.